Hello and welcome to another lecture on HCI 509, Research Methods and Statistical Analysis. In this lecture, Lecture 7, we'll talk about experimental design with multiple independent variables. Let's start with a couple of questions. From last lecture, we talked about within group and between group design. The question is, which one is better? Is within group better than the between group design? True or false? Well, we can't say that with certainty because there's no better or worse design choice, as we talked about towards the end of last lecture. It's really about what you want to study, the effects you want to try to mitigate, such as the learning effect or fatigue, and what it's possible to accomplish with your study. Here's another question. Which of the following is a characteristic of true experiments? I'll give you a moment to look these over. Now, dependent variables are measured quantitatively. Now that's important because we talked about that in our last lecture, where quantitative measurement allows us to do statistical significance tests. We also want to be able to analyze our results and use some kind of statistical significance to show that one is different than the other. Remember, this gets back to our hypothesis test, which states that there's a null and alternative hypothesis. The other one is the replication or the replicable situation under different conditions and groups. Remember, when we make a statement, we are making it about a population, but we're only able to do and conduct our study with a sample. We want to make sure that that sample that we choose is representative of the overall population. We don't mean population as the entire world necessarily, but if I say, for example, fifth graders learn better online using games than they do in the classroom, then the population is fifth graders. We want to make sure that this can be replicated by other researchers as long as we have them follow the same experimental design. The answer is all of the above. All three of the above are important to a true experiment. A third question. The basic structure of an experiment can be determined by the number of dependent variables being investigated, the number of independent variables being investigated, the number of different values for each independent variable. So is it A and C, or B and C, or one of the three choices? The answer is B and C, because the number of dependent variables, that doesn't really influence our structure as much as B and C do. And we talked about this in lecture 6. Now we talk more about factorial design. Remember, we had a basic design when we had one single independent variable that we were looking at. Now we're looking at multiple independent variables, and we talk about how we design our studies. So with the factorial design, it's widely adopted that when an experiment investigates more than one independent variable or factor, the experiment groups or conditions are divided into multiple subsets according to their independent variables. This allows us to look and investigate the impact of all independent variables as well as their interaction effects between multiple variables. We'll see some examples later on. You may recall that in the last lecture, we were discussing an experiment where we're trying to use speed to be our dependent variable, and we had two independent variables. One is the use of the device, whether it be a joystick, a mouse, or a trackball, and we were trying to identify the speed at which we could identify fonts that were large, small, and medium in size. In that case, we had two independent variables, and each one had three different categories. So we had a 3 times 3, or 9 different conditions that we had to evaluate. So the equation is given below. So here you have C, which represents the number of conditions, is the product of all the possible variables. So these are the number of levels in each variable, and you've got multiple variables. So in the condition, so if you remember that study about the trackball, the joystick, and the mouse, and the 3 different font sizes, we'd have to come up with the product of each of those. So that's where we get 3 being the number of independent variables for the type of device as well as the font size. So that's 3 times 3, or 9. Here's an example. So we had the 3 different types of keyboard. If you remember, we had the Dvorak, the QWERTY, and the alphabetically ordered keyboards. And also we want to evaluate the effect of different tasks. We could have one where we're doing composition and another one where we're doing transcription. So we have 2 independent variables, they're bolded, and then we have 3 different types of keyboards and 2 different types of tasks. So we have 2 times 3, or 6 different conditions we have to evaluate. So here you can see this might be how we would divide up the tasks. So for composition, you can see 1, 2, 3, transcription 4, 5, 6, and that's how we come up with those 6. So in the first, they complete composition. Second one is transcription. When we're analyzing the data, the conditions in the same row can be compared to evaluate how well they do on a particular type of task. And the columns can be evaluated in terms of the effect of the task itself, composition versus transcription. So either a between or within group can be adopted. With between, they complete tasks under one condition. So it's going to be one of those 6. So we'd have to divide up the pool of participants into 6 groups, and each one would do a single condition. A within group, we would have participants complete tasks under all 6 conditions. So no matter which one we choose, we have to do some kind of counterbalancing. This would be randomly assigning participants to the between group conditions and randomly assigning the order that participants complete the 6 tasks is in within group. So there's some random assignment that's going to be done regardless of our design. There's something that's interesting about doing the factorial design, and that's the split plot design. A split plot design is where we have a option that kind of is between and within. What this does is it has both components, and some variables we investigate using between group and some with a within group. So for example, we may have an experiment with 2 independent variables, age and the use of GPS. The age has 3 levels, and the second variable has 2 levels, whether they have a GPS or whether we don't use it. As we may expect, we have 6 different conditions, and the impact of age is investigated between group design because we can't change a person's age, so it would not be possible to do a within group. The use of GPS can be evaluated within group, so we could ask somebody to use a GPS and not use GPS and then determine the difference between them in terms of performance. But of course, we've got to randomize whether they begin using with a GPS or whether they begin not using a GPS as their first task. But a split plot design is one where we use both components as we see here, and we would compare 1 with 4, 2 with 5, and 3 with 6. So we go in columnar order. There's something else we got to consider, and that's the interaction effect. The interaction effect is it allows us to look at the effects of 2 or more independent variables. It looks at the effect of one independent variable on the dependent variable, and depending on the level of another independent variable. So when we have a significant interaction effect between x and y, it means the dependent variable z would be determined jointly by x and y. So we'll see some graphical examples shortly, including one from my own research. So here's an example. We conduct an experiment that investigates how types of device and experience impact the effectiveness of target selection tasks. So two types of users are studied, novice and experienced. And of course, we've got to define them a little bit better than here, but for now, we're just going to use them as two different groups. And then the diagram based on the data collected show the following. So we have novice and experienced, and we have, as our colors of our lines, we have mouse and touch screen. So the number of targets selected per minute is over there on the y-axis. And we can see here better performance is higher up in the chart on the y-axis. So it looks like novices do better with touchscreen and experienced users do better with the mouse. And you can see here that the mouse is not universally better, the touchscreen is not universally better, and we can say that there's an interaction effect because the lines cross. Again, we can see that they, depending on their level of experience, they're going to be better suited for one of two different types of devices. The target selection speed increases for both the mouse and touchscreen as they get more experience. Looking at where the novice is relative to the experienced user, you can see for the touchscreen, as they get more experience, the slope of that line increases. And for the mouse, you can see that between novice and experienced user, that line has a steeper slope, which indicates that they perform much better as they gain experience relative to the touchscreen. So here's one from my own personal research. It has to do with hiring bias. So I recently ran a study to determine hiring biases due to age, race, and gender. So age is divided into two categories. We have young professionals, which are 35 plus or minus 5 years of age. This is randomly determined. And old, which is 55 plus or minus 5 years of age. We took some resumes from different candidates that we scraped online, and we grouped them into two categories, either old workers or young workers. And we studied these two because young workers who are roughly 35 years old have different abilities and there's different expectations on them than old workers. So we grouped these into two different categories, and then we had 3 different races and 2 genders. So then we had some participants, which we got from Amazon Mechanical Turk, to evaluate these resumes. So they might get a resume that has a young black male worker, and they're going to decide whether they would bring that person in for an interview based on their resume. Then we would take the same resume, change a little bit of information, and maybe make that an old Asian female, and we would see whether they would be likely to invite them for an interview or not. The idea was to see which of these 3 categories, these 3 independent variables, would be the ones that are the most deterministic for whether they would be invited for an interview or not. So how many factors do we have? And how many categories do we have for each? Well, we have 3 factors, 3 independent variables. We have 2 age groups, 3 races, and 2 genders, which means we have 12 categories. If we do a study that looks at 12 different categories, this can be tricky because if we look at 12 categories, we've got to have quite a few participants to evaluate these resumes. So we did a between groups design for this. And what that did is it minimized the learning effect. So we didn't have to have the first person they evaluate, the second person they evaluate, etc., is going to change because they have information about who they've already looked at. And that's going to have some kind of learning effect because imagine this. You go to a dating website and the first person you see, you're going to make a decision whether you ask them out on a date or not. One thing that we might consider is that person good or not? But if you look at a second person and a third person and a fourth person, you're going to kind of see what the dating pool's like. And this is going to affect your decisions going forward. If you only see one candidate, it's going to be very challenging for you to know, relatively speaking, how well the other candidates appeal to you. So this is the learning effect in action. But it increases personal biases, but that's kind of what we want to look at. We want to see how people evaluate these candidates based on these three different factors. We hired a bunch of people from Mechanical Turk. We trained and calibrated the results. So we would ask them to make some decisions on some training samples and then give some feedback in terms of what experts would do. So this kind of calibrated their answers and allowed them to see how others would be expected to evaluate these same resumes. These people were hired from Mechanical Turk. We came up with a random combination of these three factors and then gave them a resume to look at. And they were going to decide whether they were going to bring that person in for an interview. And they were making a binary decision, either yes, bring them in, or no, don't. So we showed different job types. We had some accounting, some IT. We had some resumes that we showed them. The categories, meaning each of those 12 categories for each participant, were determined at random. So I use a tool called Excel Stat. And Excel Stat evaluates the different combinations. And here is something that shows how they are for accountants. So I'm looking at an ANOVA, which we'll talk about later in the course, but I'm looking at the different values. So here's my table that shows here are the interaction effects that we just talked about. And graphically, we can take a look at them down below. This tool does a nice job of showing these interaction effects. Here we can see this is not an interaction effect, but this just looks at how race, and again, this is how many of the candidates were rated as, let's bring them in for an interview. You can see for Asians, it's about 67%. For Black, it's about 64%. And for white, it's just under 68%. So we can repeat that with different types. Here we're doing a look at race, Asian, Black, and white. And then the line refers to whether they're male or female. So here, because they cross, there's an interaction effect. So for Asian females, they are given a higher score than Asian males. However, for Black and white candidates, the male candidates were given a higher, let's bring them in for interview score or percentage than the females. And that's also true here. And because there's a difference, we can say that race has something to do with whether they're brought in for an interview as well as gender. So there's some kind of interaction effect. Here's another one. This one doesn't have an interaction effect, but comes close. So you can see here for Black candidates, they are almost rated, whether they're old or young, as liked at almost 70%, 65%. And for Asians, you can see here, young people are favored more than older Asians for this type of job. And for white, it's almost the same amount with a slight favoring for younger candidates. So if we look just at gender, this is looking at a single factor. You can see that males are rated higher than females. And then when we look at gender and race, again, before we looked at age and race, this is looking at gender and race. You can see here for Asians, females are rated higher, but for other races, males are rated higher. And so this is an interaction effect because the lines cross, which means the combination of the two has some information that we're able to tease out. So if we look at gender and age, there's no interaction effect, which means that young people are favored regardless of female or male, the young people are favored much more than the older applicants or candidates. If we look at age, it's clear that younger candidates are favored over older candidates for accounting jobs. And here we have an interaction effect because here we have older and younger, but here we have race. So it looks like the younger Asians are favored more than the older Asians. But the others, you can see here, the effect is not as dramatic. Sure, there's more favoritism towards younger candidates than the older ones, but it's not as significant as it is for the Asian candidates here. And age and gender, we can look at the interaction effect here. Because there's no cross line, we can say that age and gender, there's not an effect from one on the other. So older or younger, male and female, it doesn't matter. It's regardless of whether they're male or female, males are preferred over females for these types of jobs, and older people are preferred less than younger people. So there's no interaction effect with these two. So we're able to tease these kinds of things out, and this is something that's nice with software tools like this, as well as an understanding. So even the use of a tool like Excel Stat is impossible unless you understand the underlying statistics behind it. So what is the importance of the interaction effect? It helps us understand the effects because performance might be affected by multiple factors jointly, but not individually. And they have implications for research design. So the chart suggests that touchscreen performs better than the mouse during the initial interaction, but they make more progress learning the mouse as they get more efficiency. And we saw, for example, that Asian females are preferred more than Asian males for this job search in terms of bringing them in for interviews. But we saw that wasn't true for blacks and for whites. We saw that males were preferred. So this gives us some information that we might not know by looking at a single factor. So again, this gives us some opportunities that we can identify that can help us understand how these implications affect the study and the research hypotheses that we're trying to look at. So again, this might imply that a touchscreen is better for brief interactions with limited training opportunities, but a mouse might be appropriate for something where you're using it all the time and you learn how to become proficient. So thank you. I hope this has been informative and helpful. I look forward to talking to you next time.